Good morning, Year 12, and welcome to another lesson on quantum physics. Today's lesson is basically looking at questions on the wave-particle duality topic. The first question is an exam question that is a multiple-choice type question, and it's asking you the following. A subatomic particle with kinetic energy E has a de Broglie wavelength lambda. What is the kinetic energy of an identical particle with a de Broglie wavelength 2 lambda? So this is actually quite a challenging multiple choice question. You don't have a huge amount of time and you've got to think pretty fast. So how do we go through this? I'll take you through it step by step. Once you get a chance to practice this, please have another go as well, just so that you can speed through it, because obviously you don't have much time with these multiple choice questions. So we need three equations. We need the kinetic energy equation, which is E is equal to half mv squared. We need our de Broglie equation as well, de Broglie wavelength equation, where the de Broglie wavelength is equal to the Planck's constant divided by the momentum. And we also know that momentum of a particle is given by P is equal to mv. So we're going to use these three equations. So substitute the momentum equation into the de Broglie wavelength equation, and we get lambda is equal to h divided by mv. Okay, and if you rearrange that to make v the subject of the equation, we get v is equal to h divided by m lambda. Now, we then need to substitute this into the kinetic energy equation. So we get E is equal to half m multiplied by h squared divided by m squared lambda squared. I've gone through all the steps just so you see how I got to these stages. Then what we notice is that one of the m's cancels. So we are left with E is equal to a half h squared divided by m lambda squared. Okay, we can write that as E is equal to h squared divided by 2m lambda squared. So let's make a formula for the different scenario where the wavelength is 2 lambda. So let's call this new energy that we're trying to work out E2. So E2 is equal to h squared divided by 2m multiplied by 2 lambda, all in brackets, squared. So E2 is equal to h squared divided by 2m multiplied by 4 lambda squared. Okay, so we have an equation for the original energy, and then we've got a new equation for the energy when the wavelength is doubled. So if we take the ratios of the two, or we divide E by E2, we get an expression on the right hand side as shown here, h squared divided by 2m lambda squared, all divided by h squared divided by 2m for lambda squared. And then we can also write that as h squared divided by 2m lambda squared multiplied by 2m for lambda squared divided by h squared. And most of it obviously cancels out. So we are left with E divided by E2 is equal to 4. Rearranging that, we get 4 multiplied by E2 is equal to E. So E2, in terms of an expression using the original energy, is E over a quarter. So in effect, doubling the wavelength will have the effect of decreasing the energy by a factor of 4. Question number 2. A student carries out an experiment to determine the value of the Planck constant using LEDs. The wavelength of each LED used is known. The student carries out the following method. Number 1. Set up the circuit shown in figure 1. Number 2. Adjust the variable resistor so that it is at its maximum resistance, so the LED does not light up when the power supply is switched on. Then switch on the power supply. Number 3. Gradually decrease the resistance of the variable resistor so that the voltage across the LED increases until the LED is seen to light up. Record the value of the voltage across the LED at this point, which is the threshold voltage. Number 4, switch off the power supply, replace the LED with another LED that produces a different wavelength of light. Number 5, repeat steps 2 to 4 for a number of LEDs that emit different wavelengths of light. The student uses their results to plot a graph of threshold voltage against 1 over the wavelength as shown in figure 2. So the graph is plotted and we have to calculate Planck's constant. Okay, so there we have a question that incorporates previous knowledge, where we did an experiment earlier on in this unit estimating Planck's constant using LEDs. So sometimes you get questions like this which are really useful, because when you're practicing you get to cover other topics from earlier on as well as the current topic, which is wave or particle duality. Another good thing about this question that I've noticed is that obviously it's got the method as well for estimating the Planck's constant experimentally. So you can use this as a guide in terms of if the question asked you, as there was an earlier question that did ask you this, how to carry out an experiment to determine the value of Planck's constant using LEDs. So you have that method there as well. Now you have a nice circuit diagram there containing an LED. You've got your power supply, a voltmeter to measure the threshold voltage. You have a variable resistor, and you have a resistor there as well, which is there in a protective capacity to protect the LED. And this can be used to give the approximate value for the Planck's constant. Okay, so you may remember this method. Basically, this experiment makes use of LEDs of different colors. You may remember that an LED conducts in one direction only, which is the forward direction, and that it requires a minimum voltage, which we call the threshold voltage, to be applied in this direction before it allows current to flow. So this experiment makes use of the fact that LEDs of different colors require different threshold voltages before they conduct and emit light. So at the threshold potential difference, the energy transferred by an electron in the LED is approximately equal to the energy of the single photon it emits. So we can therefore say that an LED will emit a photon with an energy E is equal to HF, which you can write as E is equal to HC divided by lambda. So this energy is equal to the kinetic energy of an electron, which is accelerated across the threshold potential difference, given by the equation E is equal to E V naught, where V naught is the threshold voltage. So we can write the equation E V is equal to HC over lambda. I should have put V naught there actually. I'll just put V, so you can add that if you would like. So V naught is equal to HC divided by E lambda. Comparing this to our equation of a straight line, which is y is equal to mx plus c, we can see that the gradient of the graph of V naught against 1 over the wavelength is given by m, which represents the gradient, and m is equal to hc over e. So h, making h the subject of the equation, is equal to me divided by c, where c is the speed of light, by the way, and e is the charge on an electron. So m, the gradient, is equal to, I've taken some points on the graph, is equal to 2.425 minus 2.22, which is the change in y, and divided by the change in x, and I've taken the corresponding points there, so that's 1.9 times 10 to the power 6 minus 1.74 times 10 to the power 6, and I get a value for the gradient of 1.28125 times 10 to the power minus 6. So I can now put that into, substitute those values into my equation, h is equal to me divided by c, and I get 1.28125 times 10 to the power minus 6 multiplied by charge on an electron, which is 1.6 times 10 to the power minus 19. All of that divided by the speed of light, which is 3 times 10 to the power 8. And that gives me a value for Planck's constant as 6.833 continued times 10 to the power minus 34 joules second, which I can write to three significant figures as 6.83 times 10 to the power minus 34 joules second. Okay, now that's my Planck's constant. So part B of question number 2. An electron passes through an LED and causes a photon with an energy of 3.06 times 10 to the power minus 19 joules to be emitted. Use your value for the Planck constant calculated in A to find the de Broglie wavelength of the electron. So hey presto, this is now into the wave-particle duality territory of the question. So what do we do? Let's see. We can say that the energy of the photon is equal to the kinetic energy of the electron. Okay. So in other words, let's write our equations down. We know that the kinetic energy of an electron is given by half MeV squared. So that Me is just the mass of an electron. Okay. And we know the de Broglie wavelength equation, which is lambda is equal to h divided by p, which we can write as h divided by me multiplied by v. Okay, because we know that p, the momentum, is equal to mv. So, rearranging to make v the subject of the kinetic energy equation, we have v is equal to the square root of 2 times e divided by me, which is equal to the square root of 2 times 3.06 times 10 to the power minus 19, okay, which is the energy of the electron as it's emitted, divided by the mass of that electron, which is 9.11 times 10 to the power minus 31, which is equal to 8.196 times 10 to the power 5 meters per second. So the wavelength, therefore, is given by, or is equal to 6.833 continued times 10 to the power minus 34. This was what we obtained for Planck's constant from our earlier calculations in part A. We divide that by the mass of an electron, 9.11 times 10 to the power minus 31, and multiply that by 8.196 continued times 10 to the power 5. Should be a bracket, closed bracket over there. Please add that along as well. Okay, just remember that the mass of an electron will be given to you in the equation sheet, so it's not something that you have to remember. But when you do it a few times, or you do a few questions using the mass of an electron, you just end up remembering it anyway. So probably save you time having to look it up in the equation sheet. But it's there as well if you need it. Okay, so you don't have to remember it. And now what we find for the de Broglie wavelength is a value of 9.1516 continued times 10 to the power minus 10 meters. Okay, so we need to just write that to three significant figures, and we get 9.15 times 10 to the power minus 10 meters. Okay. Then the question continues on to part C, and it says the student alters their circuit to include a milliammeter as shown in figure 3. So they've added a milliammeter to that circuit. The student repeats the experiment, but this time they record the threshold voltage as the value of the voltage across the LED when the reading of the ammeter begins to increase, as opposed to what they were doing before, which was just using their eyes to detect when the light turned on. They then use these results to calculate a new value of the Planck constant. So C asks you, suggest how the student's new value of the Planck constant will compare with the initial value from A and the true value of the Planck constant. Explain your answer. So for the first mark, we can say the new value will be closer to the true value of the Planck constant than their initial value. Okay, and the reason for that is, for the second mark, that the student will be able to determine when the LED reaches the threshold voltage more accurately. That's the key bit there, as they will be able to determine exactly when more current begins to flow through the LED, rather than having to rely on their judgment of when the LED lights up using their eye. Okay, so that's an explanation question there worth 2 marks, and that concludes that particular question. Question number 3, part A. In atomic physics, electron energies are often stated in electron volts, EV. Define the electron volt and state its value in joule. So let's imagine you've got some parallel plates, and you've an electron down there at the bottom, and you've got the other plate that is positively charged and has a potential difference of 1 volt. So if this electron is attracted to the positive plate, it will gain, as we know, kinetic energy, and will be traveling faster up as it gets or as it approaches the positive plate. So we're talking about an electron accelerated through a potential difference of 1 volt. Electrons, as we know, have a negative charge, so they'll be attracted to the positive plate. If the plate with the electron has a potential difference of 0 volts, the top plate has this potential difference of plus 1 volt. There is an electric field created between the 2 plates, so we know that the electron will gain energy, and it gained 1 electron volt of energy. That energy is equal to what we call the electron volt. So we also know that E is equal to QV. Okay, so we can say that 1 electron volt is the energy gained or required by an electron that is accelerated through a potential difference of 1 volt. Okay, on to part B. An electron is accelerated from rest through a potential difference of 300 volts. Part 1, calculate the final kinetic energy of the electron in electron volts firstly. So if 1 volt accelerates the electron to 1 electron volts, then 300 volts will accelerate that electron to 300 electron volts. So the answer is 300 electron volts. Part number 2, in joules. Okay, so calculate the kinetic energy of the electron in joules. Remember that 1 electron volt is equal to the charge is equal to 1.6 times 10 to the power minus 19 joules. So we can say that the energy gained is equal to QV. In this case, Q is the charge of an electron, so we can put it down as E. So we get E multiplied by V, and the energy is equal to 300 multiplied by 1.6 times 10 to the power minus 19, which is equal to 4.8 times 10 to the power minus 17 joules for the kinetic energy. Okay. On to part 2 of B. Show that the final speed of the electron is about 1 times 10 to the power 7 meters per second. I do like these sort of questions because they've given you the answer, so you know what to expect. So we know that the kinetic energy, which I've called EK, is equal to a half mv squared. If we make V the subject of that equation, we are left with V is equal to the square root of 2EK divided by M, where M is the mass of the electron. And V therefore is equal to the square root of 2 times 4.8 times 10 to the power minus 17 divided by the mass of the electron, which is 9.11 times 10 to the power minus 31. And that 4.8 times 10 to the power minus 17 is what we obtained for the energy of an electron from part B 1. Okay. So the value for V is equal to, we get on a calculator, 10,265,413 meters per second, which we can write down as 1.03 times 10 to the power 7 meters per second, which is approximately equal to 1 times 10 to the power 7 meters per second. Now, if it's a show question, as I said, I quite like those questions, and because we can see where we're going or what we need to get to. Now, we've got to find the answer to 3 significant figures if we want to show that it's equal to 1 times 10 to the power 7. So make sure that you write your answer to 3 significant figures first, just to show that it is approximately equal to 1 times 10 to the power 7 meters per second. Don't just write 1 times 10 to the power 7 meters per second. As I say, just make sure that you write the value first to 3 significant figures, so you can show that when you round it up, you do get 1 times 10 to the power 7 meters per second. Okay. On to C, part 1. Explain what is meant by the de Broglie wavelength of an electron. This is worth 2 marks. So to get the first mark, electrons are observed to have wave-like properties. Okay, that's your first mark. Your second mark would be to say that the wavelength depends on their momentum in the following relationship, i.e. the wavelength is inversely proportional to the momentum. Okay, so that will get you your second mark. There is another way of defining this as well, so it's just a case of which you prefer. Sometimes they don't ask for you to explain what is meant by the de Broglie wavelength of an electron. They sometimes ask you to explain what is meant by the de Broglie wavelength of a particle. Okay, so in that case, depending on which it is, you could either say an electron or a particle moving through space has a wavelength lambda given by the de Broglie equation. Lambda is equal to h divided by p, where h is the Planck's constant and p is the momentum of the particle or the electron, depending on which they asked you to explain. Okay, so either of those two definitions would be fine. Just depends which one you prefer. On to part 2, calculate the de Broglie wavelength of the electron in B. Now remember, from B part we did have a value given because we had to show that the velocity was 1 times 10 to the power 7 meters per second, I believe it was. So even if you weren't able to calculate that value, you mustn't leave out this question, because you've been given from part B the value of the speed of the electron. Okay, so make sure you use that if you didn't work it out. So we know that lambda is equal to h over p, which we can write as lambda, the de Broglie wavelength, is equal to h divided by mv. So Planck's constant will be given in the equation sheet, and so will the mass of an electron, but both hopefully you'll be able to remember anyway, having done them many questions in preparation for your exam. So lambda, the de Broglie wavelength, is equal to 6.63 times 10 to the power minus 34 divided by 9.11 times 10 to the power minus 31 multiplied by a value calculated from part B for the velocity, which is equal to 1.03 times 10 to the power 7, gives you a value for the wavelength of 7.09 times 10 to the power minus 11, which we can write as 7.1 times 10 to the power minus 11 meters. Okay, there we go. Okay, question number 4. The concept of wave-particle duality is supported by experimental evidence. The photoelectric effect demonstrates the particle properties of light. In terms of particle interactions, describe the phenomena observed during a photoelectric effect experiment. Explain why these observations cannot be explained by considering light as a wave. So this is another interesting question, because before we talk about wave-particle duality in this question, they are first looking at the photoelectric effect. So this, as I said, photoelectric effect is the topic which seems to come up in the exams on a regular basis. Okay, so make sure that you're aware of this particular experiment. So you can get 3 marks if you can first of all describe the observations of the photoelectric effect experiment. Okay, so let's try and tackle that first. A little diagram there just to remind you. We have this incoming photon of light, which has an energy E is equal to hf. Okay, it's behaves like a particle in this experiment, light does. And if it's got enough energy, and if the frequency of the incoming photon is greater than the threshold frequency, then we get the emission of a photoelectron from the surface of the metal. So let's try and describe this in bullet points. So we have a stream of photons is incident upon a sheet of metal. A photon incident on a metal may interact with a free electron in the metal and be absorbed and transfer energy equal to its total energy, E is equal to hf to that electron. Okay, that's what happens next. Then, if the photon's frequency is high enough, i.e. above the threshold frequency, it will transfer enough energy to the electron that it is able to escape the metal. Okay, and this is what we call the photoelectric effect. All right. On to the next part, which is where we have to explain how these observations cannot be explained by considering light as a wave. Okay, so we need to talk about this experiment observations in terms of the wave model and how the wave model, what the wave model says and how it doesn't apply to this, to what's happening in this experiment. So the first thing we can say, according to the wave model, if light were a wave, it would deliver a continuous stream of energy, a continuous stream of energy if it was a wave. But we know it's not that, that's not the case. It's discrete packets of energy that are delivered. So the total energy transferred by a wave would depend on the time for which the wave was incident on the metal surface, so how long the light is incident on the metal surface, the intensity or the brightness of the wave, and it also depends on the frequency of the wave. Okay. So intense enough light or light that is incident for long enough should be capable of causing photoelectric emission or the emission of photoelectrons regardless of the frequency of the light. But as we know, that's not the case. It all depends on the frequency of the light. Okay. However, no photoelectrons are emitted unless the frequency of light incident on the surface exceeds a certain threshold frequency, and that is regardless of the intensity and length of time of the light shining on the plate. Okay. Also, if light were a wave delivering a continuous stream of energy, you would expect an increase of light intensity to lead to photoelectrons being emitted with greater kinetic energy, but that is not the case. However, what we actually see is that the maximum kinetic energy of emitted electrons does not increase, even if we increase the intensity of the light that is incident on the surface of the metal. Okay, so increasing the light that is incident on the surface of the metal does not increase the maximum kinetic energy of emitted electrons. Okay, and that should be enough to get you your 6 marks. All right. Part B of question number 4. It is possible to observe subatomic matter behaving in a wave-like manner. For example, neutrons may diffract as they pass through a silicon crystal. Explain why it is not possible to observe much larger objects behaving in this way. Aha, this reminds me of when we looked at people waves. So we know that we can apply the de Broglie equation to all matter, anything that has a mass, so including people, including golf balls and so on. So we did look at an example of a person, and we found that the wavelength of the person was something in the order of 3.4 times 10 to the power minus 36 meters. So an extremely small wavelength. Okay, this wavelength is very, very small compared to the size of the gap. Okay, we had a gap, I think, of let's say 0.8 meters, the gap being, let's say, a doorway. And that's why we weren't able to see diffraction effects, because people cannot be diffracted through everyday gaps. The de Broglie wavelength of this person, let's say of 65 kilograms, is much smaller than any gap the person is likely to try to squeeze through. So for that reason, we do not use the wave model to describe the behavior of people. We get much better results by regarding people as large particles. So how do we answer that for 2 marks? Let's see. We can say that much larger objects will have a much smaller de Broglie wavelength. Okay. So there's just no gap that exists that are small enough to match that particular wavelength, because for diffraction to occur, the gap must match the wavelength, okay, of that particle. And so, because no gap exists that are small enough to match this wavelength, they cannot allow diffraction to occur. Okay. On to part C. A physicist is investigating the arrangement of carbon atoms within graphene, which is a form of pure carbon. She uses a potential difference to accelerate free electrons that are initially at rest through a vacuum and towards a slice of graphene. She gradually increases the accelerating potential difference until she is able to observe evidence of the electrons diffracting as they pass through the graphene. She first observes the diffraction pattern when the potential difference is equal to a value of 75 volts. So calculate an estimate of the separation between the adjacent carbon atoms in the graphene. So we can use equation E is equal to E multiplied by V, and we get 1.6 times 10 to the power minus 19 multiplied by 75 volts, which gives us a value for the energy of 1.2 times 10 to the power minus 17 joules. Then we can use our kinetic energy equation, E is equal to half mv squared. Making V the subject of the equation, we get the square root of 2E divided by m is equal to the velocity, which is equal to the square root of 2 times 1.2 times 10 to the power minus 17 joules divided by the mass of an electron, which is 9.11 times 10 to the power minus 31, which gives a value for V as 5.13 continuous, multiplied by 10 to the power 6 meters per second. Then we use our de Broglie wavelength equation, lambda, which is equal to h over p, which is also equal to h divided by mv. So the de Broglie wavelength is equal to 6.63 times 10 to the power minus 34 divided by 9.11 times 10 to the power minus 31 multiplied by 5.13 continued times 10 to the power 6, which is equal to 1.41 times 10 to the power minus 10 meters. Okay. So with these questions, just be careful because obviously electron volts we know are much more useful than joules when it comes to thinking about the tiny amounts of energy emitted and absorbed by electrons. However, the all-important relationship E is equal to HF only works, please remember, if you input an energy that is in joules, okay? But as we know, we don't have to despair because all we need to do to convert from electron volts to joules is multiply by 1.6 times 10 to the power minus 19, okay? So that's the answer to that question. On to question 5. This question is about electrons and photons. That's good, we love that. And part A, both electrons and photons can be considered as particles. State 2 differences between their properties. Okay, I'll give you 3 just so that you have more options available to you. So the first difference we can certainly say is that electrons have mass, whereas photons do not have any mass. Also, electrons are negatively charged, so they have a charge, whereas photons have no charge. And the other one is that the electrons travel at a speed that is less than the speed of light, whereas photons travel at the speed of light. Okay, good. On to part 1. An electron is accelerated from rest through a potential difference of 5,000 volts. Show that the energy gained by the electron is 8.0 times 10 to the power minus 16 joules. So we know that the energy gained is equal to the elementary charge multiplied by the potential difference. Okay, and so we can say that the energy gained is equal to 1.6 times 10 to the power minus 19 multiplied by 5,000, and that gives us 8.00 times 10 to the power minus 16. Okay, remember we've got to write more significant figures than what is being asked to be shown, so I've added some more numbers there for you, and then we can approximate that to 8 times 10 to the power minus 16 joules. So I've put there 3 significant figures, and then I've rounded it up to show that that is indeed equal to 8 times 10 to the power minus 16 joules. On to part 2. Show that the speed of the electron is about 4 times 10 to the power 7 meters per second. They're really going for the showing questions here on this one. So what do we do? Well, the kinetic energy we know is given by half mv squared. So we've done this quite a few times. We need to rearrange this equation to make v the subject of the equation. Again, as I said, we've done that a few times. And so we get the v is equal to the square root of 2ek divided by the mass of the electron. Let's plug in our numbers and we get to the square root of 2 multiplied by 8.0 times 10 to the power minus 16 divided by the mass of the electron, 9.11, times 10 to the power minus 31. Okay, it gives us a value of 41,908,373.21, which we can write again to 3 significant figures, because we've got to have more significant figures than what the thing is that we have to show. So 4.19 times 10 to the power 7, which we can approximate to show that it's equal to 4 times 10 to the power 7 meters per second. Okay, so just notice that we do get a lot of these questions, so we should quickly be able to remember how to make v the subject of our equation from the kinetic energy equation. Okay, make sure that, as I say, always writing more significant figures than what is actually being asked to be shown, and also just also make sure that you remember the differences between photons and electrons. Okay, and that's the end of that particular part of this question. We'll move on to the next parts. Okay, question 5c, part 1. Explain what is meant by the de Broglie wavelength of an electron. That's an old chestnut again that we are revisiting. We did this earlier. So we should remember that electrons are observed to have wave-like properties. For the first mark, the wavelength depends on their momentum. Okay, so we know that the wavelength is inversely proportional to the momentum. We can also say a particle, or in this case an electron, moving through space has a wavelength lambda given by the de Broglie equation. Lambda is equal to h divided by p, where h is the Planck constant and p is the momentum of the particle, or in this case electron. So you don't have to write both definitions, one or the other would do. Okay, right, on to part 2. Calculate the de Broglie wavelength of the electron from earlier in B. Now the good thing about this question is, again, that if you can't do one part of the question, remember, because 2 parts were actually asking you to show a certain value, you can use those values that are already given to you in order to answer the questions later down the line, even if you couldn't get the you couldn't show those particular values. So make sure you don't leave these questions out just because you weren't able to show those particular quantity values. Okay, so let's work on this one then. We know that de Broglie wavelength is given by the equation h divided by mv, and so we can plug in our numbers. The de Broglie wavelength is equal to 6.63 times 10 to the power minus 34 divided by 9.11 times 10 to the power minus 31, multiplied by something that we obtained earlier, which was the speed of the electron, 4.19 times 10 to the power 7. Okay, and that gives us a value for the wavelength of 1.7 times 10 to the power minus 11 meters. Okay. Part D, calculate the wavelength of a photon which has an energy of 8 times 10 to the power minus 16 joules. Okay, so the energy of a photon is equal to hc divided by lambda. Okay, so we've already been given the energy of a photon in joules, so we don't have to convert from electron volts to joules at all. It's already there for us, so that makes it more straightforward. The wavelength, rearranging that equation to make wavelength the subject of the equation, is given by hc divided by the energy of a photon. So plugging in the numbers, the wavelength is equal to 6.63 times 10 to the power minus 34 multiplied by 3.0 times 10 to the power 8. Divide that all by 8.0 times 10 to the power minus 16, and we should find that we get a wavelength of 2.5 times 10 to the power minus 10 meters. Okay, now part E. Photons of energy 9.0 times 10 to the power minus 90 joules are incident on a clean tungsten surface causing electrons to be emitted. Aha! State the name of this process. Now that's a nice, easy 1 mark to get. Well, we know for sure that that process of photoelectrons being emitted from the surface of a metal by incident photons that are having a high enough frequency above the threshold frequency of that particular metal, tungsten in this case, is called the photoelectric effect. Okay, there we go. Okay, so part 2, we have to calculate the maximum kinetic energy of the emitted electrons. Tungsten has a work function of 7.2 times 10 to the power minus 19 joules. So this question really is delving into our knowledge of the photoelectric effect. So we need to remember our important equation, which is the energy of a photon is equal to the work function plus the maximum kinetic energy of the electrons. Now, this is, of course, Einstein's photoelectric equation. So, rearranging that to make the kinetic energy of the electrons, the maximum kinetic energy of the electrons, the subject of that equation, we have Ek max is equal to E of a photon, take away the work function. So, Ek max is equal to 9.0 times 10 to the power minus 19. Take away 7.2 times 10 to the power minus 19. So the powers are the same, so that should be an easy subtraction. And we are left with a value for the maximum kinetic energy of 1.8 times 10 to the power minus 19 joules. Part 3 is slightly more challenging. Explain why your answer to part 2 is a maximum value. Well, the electrons emitted have, as we know, a range of velocities up to the value of 1.8 times 10 to the power minus 19 joules. Now, most of these electrons require more than the energy of the work function in order to escape. So some might need a little bit more energy for that to happen. Okay, and that's your second mark there. And that's the end of this session, really. The only thing I would just like to advise is the more past papers you do, the more you'll see the same kinds of questions coming up. So just being able to do the same types of questions over and over again, it will almost become second nature to you if you can invest the time in doing that. Okay, I would suggest you can do more than this, of course. I wouldn't suggest much less, but if you just put an hour a day over the holidays if you can, and subsequent days to come, if you can put an hour a day, not every day, let's say for 5 days a week, then I think that would stand you in good stead, practicing past papers. Okay, and then once you've spent, that's what, 5 hours a day just for this subject, you've got maybe 2 other A-levels to do, so you're looking at about 3 hours, maybe 4 hours of work a day for 5 days a week. Would really help you to get very good grades, I'm sure, because as I said, once you practice the questions from the past papers, the more that you do, you'll be doing questions that are very similar, and it'll all become second nature to you, and you'll get faster at it. You recognize what is being asked, and you'll be able to tackle all those questions in the exam. Okay, so do go through these questions again. Okay, I would advise you to do that for your preparation for your test on this unit, and I'm sure that you will do very well. Okay, so have a great day and see you next time.